Recording is rolling. It is Wednesday, September 25th. We're going to take today to solve as many of these textbook puzzles as we can. So I'm doing this with each of my classes. Now, you guys, your textbook is organized. This is from your conceptual physics book. It goes chapters 4 through 6. Each chapter is a law of motion. You've got first law, second law, continues up here, and then the third law. The questions approximately correspond with the laws, right? There's some force questions, some other type questions. Okay. All right, so I wrote this morning. I said, if there's school tomorrow, there's gonna be out. Well, you guys probably got the news by now. There's no school tomorrow, right? And Friday, it's still an open question. We'll keep an eye on the news. There may or may not be school Friday. If there is, we'll at least get started on this Atwood lab. If not, then well, going back to Monday. All right. So can you guys check focus, make sure you got everything turned in, you're not missing anything. I'm still waiting on a few projectile quizzes for each of my classes. Helene, I guess. Is that how you say it? Hurricane Helene? Helene?
It's Greek. It's actually my middle name in Greek. Helene.
All right. Pretty good. All right. Hurricane Helene. Helene. All right. All right. So here we go. You guys got some paper Let's do. We'll start with the first law of inertia, right here. And so everybody's got some paper. All right. I'm helping you guys do your work right here. Ooh, yeah. I didn't realize on my computer screen how these didn't look so small there, but that's okay. We can still read them. Number 27. Lucy Lightfoot stands with one foot on one bathroom scale and her other foot on another bathroom scale. Each scale reads 350 newtons. What is Lucy's weight? So here we go. This is, we'll call this chapter 4. Chapter 4. All right, you guys write on paper. You guys write your name. You guys write chapter 4. You guys write your name on your paper. Chapter 4. Okay. This is number 27. So let's get a picture of Lucy Lightfoot. She's got one scale here, one scale here. Right. Let's do a. Okay. Give her a ponytail. How about that? Let's do a free body diagram. On Lucy Lightfoot. Okay. No, there's one force from each foot, which I normally ignore that detail, but here it's gonna matter. So it's 350 newtons from each one. So we got normal force from that scale is 350 newtons. Normal force from this scale is 350 newtons. Right? Therefore, what is her weight?
350.
Huh?
400.
700 newtons. There you go. The guiding principle is the sum of forces is 0 newtons. Right? So the two upwards have to cancel with the downward. There's your answer right there. Everybody's got number 27. Everybody's got it. Everybody wrote that on paper? Right? Everybody's got some paper. So I'll eventually pick this up from you, give you points. All you gotta do is write it down. Number 28. So number 28. Zoom in here. Henry Heavyweight. I guess they're all alliterative names. Weighs 1,200 newtons and stands on a pair of bathroom scales so that one scale reads twice as much as the other. Ooh, what are the scale readings? Ooh, it sounds kind of similar, but takes a little bit more thinking. So let's get Henry Heavyweight. Scale, center mass. Right? So if one scale reads twice the other, here I'll go ahead and kind of try to draw it that way. One scale is twice the other. That could be like that, right? Oh, here we go. Tell us force left and force right. Maybe I could do that. Right? Force left and force right. Okay. And his total weight, mg, is, let's say, 1,200 newtons. 1,200 newtons. Right? So there's different ways you could solve this. One way you could do trial and error. Say, well, what if it's this set of numbers or this set of numbers? So you could do until you get a 2-to-1 ratio that I guess adds up to 1,200. That would make sense, right? So he's kind of leaning on the scale. So you guys see that, right? He's kind of leaning one way so that there's more force on one side than the other. All right. Now, if you want to do this properly mathematically, you need a system of equations. You guys see how there's two unknown values? We don't know the force rating from each scale. Right. So I could say, here's my system. Force left plus force right equals, how much help is it going to equal? 1200 newtons. Yeah, you can do that too. Yeah, so that's another way. You just divide 1200 by 3. Right. I'm showing you guys a maybe more like systematic way to go about it. Because what if it was like a crazy ratio or something like that? Sure. Yeah. All right. Or you could say the forces added minus 1200 equals 0, really. And the other equation you need is the ratio of the forces. So I could say, what did it say? What is this? What are the scalar readings? Yeah, scale readings. Well, look at both of them. Yeah. So this ratio is 2 to 1. Okay. This right here is your system and algebra. Right. So you guys read that? Okay. Right. So, true. If you could see the big picture and so we guys said it's like, oh, we could just divide by 3 and kind of get to the answer real fast, right? That's okay too, right? I'm going to do this way, where I cross multiply. Can I take this equation right here and write it as therefore the right force equals 2 times the left force, or that maybe I could have started that as my second equation. Okay. Then I'm going to substitute that. I'm going to take this right here. I'm going to substitute that right there. Right. So what is the right force? Well, it's 2 times the left force. I could just substitute there. Right. Right. Now let me write a new line right here. Is that left force plus, and then instead of saying the right force, up here I'll put in brackets to show that I'm doing substitution. 2 times the left force equals 1200 newtons, or 3 times the left force equals 1200 newtons. Okay, so we got that so far. Okay. That's where you guys are saying, hey, you just divide by 3, right? And then that's the math that backs up why you can just very simply divide by 3. That's true. Right. Right, are we good? Right. So I ran out of paper here, so I'm going to flip the well, here, maybe I'll do it this way. I'm going to slide this up and I'll continue it right down here. Right here. Right. Again, this is the way I'm solving it here is kind of a systematic approach to it. So divide both sides by 3. Therefore, left force equals that. Guys, what's 1200 divided by 3? Is that 400 newtons? Right, 400 newtons there. Right. Now, if I want to get the right force, I have an option. I can pick either of these initial equations and solve for the right force, and they should both tell me the same thing. Or I guess I could pick one of them, solve it, and then check my answer with the other one. Right? So, hey, what if I take this circled substitution right here? Remember before I wrote the right force equals 2 times the left force. And maybe you can kind of see this intuitively, hopefully too, maybe from the picture anyway. But this is a systematic way to go about it. And then since my left force was 400 newtons, it'd be 2 times that. Therefore, what's the right force equal to? Put it all together. 800 newtons. There it is. Boom, boom. Right. All right. So last check. I need to go back and check the other equation. So I know it's a 2 to 1 ratio. I just used that to solve for the other force. But what about the equation that says that the 2 forces have to add up to 1200 newtons? Or you could say, you add them up and then subtract the 1200 newtons, it zeroes out. Think of it that way. Right. So is that true? 400 plus 800? Yeah. 400 newtons plus 800 newtons is in fact 1200 newtons. Check. So it worked. So we're all good. There's the whole thing. All right. You guys good on Henry Heavyweight? All right, number 29. We got a sketch shows a painter's scaffold and mechanical equilibrium. Look at this. He's standing on the scaffold. Looks like he weighs it's at 500 newtons. Right? And then there's 400 newtons and 400 newtons. But wait a minute, they've got to be leaving something off. Let's go back to this premise. The person in the middle weighs 500 newtons. each tension is 400 newtons, 400, 400, right? What is the weight of the scaffold? That's what they're leaving off, the weight of the scaffold. Now, guys, do you think the weight of the scaffold is distributed over the entire length of the scaffold? Yeah, right. Do you think it's perfectly okay to mathematically treat this as those acting at the center, like the center of mass, right? Actually, I'm getting a little bit ahead. I'm thinking a few months ahead when you guys are gonna solve a torque, but this one's a little bit more straightforward than that even. Right? This one, all you have to do is say the sum of the forces is what is the sum of the forces for anything that's at rest? 0. Yeah, 0. So 0 newtons. So number 29. So it's gonna go like this. The upward tension. So, well, the left tension plus the right tension, which are the same. So tension, right tension, right? Minus the weight of the person. So I'll do mg of the person. Minus the weight of the scaffold. Equals 0, and that's newtons, right? That's the full proper equation for that, right? 2 upward forces, 2 downward forces, it has to zero out. Right? Now they gave you 3 of those numbers. They said, well, this is 400 newtons here. Bing. This is 400 newtons here. Bing. The weight of the person down is 500 newtons, so being subtracted. Bing. Now what's the weight, mg, of the scaffold? Does that make sense? Right? Is that okay? Here's that. Guys, what's 400 plus 400? 800. 800 minus 500 is 300. 300. Right. So that has to be the weight of the scaffold then. Yeah. So the weight of the scaffold.
What?
Is 300 newtons. Oh yeah. Right. So yeah, 400, 400 up. We got 500, 300 down. So it's 800 up, 800 down. Yep, it definitely zeroes out. I guess the guiding principle, maybe I should have written this first, is this. The sum of the forces goes to 0 newtons. Okay. There you go. So you got the scaffold. Right, you guys get on the scaffold. All right. Oh, looks like it's got shuffled around, but you know what? Here, there's another scaffold right here next to it. It's number 30. It's this one. A different scaffold. We've got a 400 Newton person. Sports. Okay, we got a 500 Newton sign painter. Another painter that's 400 Newton. Okay, and the reading the left scale is 800 newtons. What's the reading on the? What's the tension in the right rope? Right, that's holding up the scaffold. Right. Now, here, but before we go plug in and check and solve this, do you guys think if this guy's walking around, do you guys think if these 2 people are walking around that the tensions are changing individually? Right? Yeah, that would. So their location does matter. Right? But this particular question, the setup, they did give you enough information where you can solve it even without considering their locations. So probably in December, I'm thinking we'll bring in like walking around on the scaffold. And there's a concept called torque. But for this one, all you need is just force equilibrium because they gave you enough information. So let's do number 30. Here's the guiding principle. Sum of forces goes to 0 newtons. Right, it's in the y direction for that matter. Okay. Yeah, so I got 800 newtons upward plus a mystery tension upward that we're solving for. Number 30. Number 30. Okay. Minus 500 newtons for that person. Minus 400 newtons for the scaffold. Minus another 400 newtons for this other person. All zeros out. There's the full setup, right? We got 2 upward forces, the 2 ropes, right? And then 3 downward forces, 3 weights, right? 2 people on the scaffold, right? And it all has to zero out. Sure. All right. So add all this bit over. That'd be 500 plus 400 plus 400, right? And then subtract off the 800 newtons tension that's already been accounted for. I'm getting a tension of 500 newtons. Boom. Okay. So we'll go back and do a check. So while you guys are finishing writing that, let's see if this works. All right, so what was going up? 800 and 500 is up. Is that 1300 newtons up? And what was pulling down? 5, 4, and 4. That's also 1300 newtons down. So 1300 up, 1300 down. It's a wash. Okay, all good. All right, next one. Number 32. Check this out. Yeah, 32. Rank the net forces on the blocks for the 4 situations. Let's just find out what they are. I think that'll be good enough. Number 32. Here we'll call them A, B, C, and D. So A, B, C, D. Okay. So we got forces pulling in opposite directions. So option A, or block A, I should say, is it 10 newtons and 5 newtons? So there's a difference. So say 10 newtons minus 5 newtons is a net force. Well, here. These are all net force equals, right? F net equals 5 newtons to the left. Block B, I see, what's that, 7 versus 3? Okay. So F net equals 7 newtons, 3 newtons pulling opposite directions. That is overall 4 newtons to the left. Okay. So this is like if there's a block sitting in the middle of the room, you got 2 people either pushing or pulling the block opposite directions. They're canceling out their efforts, right? Like if they both push the same direction, they could really get that block scooting in one way. But if they're pushing opposite, it's kind of like canceling out, sort of. Right? Maybe not completely if one guy's pushing harder than the other guy. Okay. Right. Block C, got 12 versus 4. F net is 12 newtons minus 4 newtons. That's like 8 newtons. And that's also left, because overall it's to the left. Okay. And block D, we got, is that 3 and 3? Okay. So F net equals 3 newtons one way minus 3 newtons the other way. That zeroes out. Right, there's 0 net force on that last one. Right, you guys got the net forces? All right. Number 33. Different materials, A, B, C, and D, rest on the table. Rank how much they resist being set into motion from greatest to least. Ooh, guys, resist being set into motion. What physical property is that? Is that inertia? Inertia? Yeah. Right. And right now, what variable do we have to quantify how much inertia? How much mass? Right? How much mass? Right? The more mass, the more inertia. Oh, yeah.
For 64, when it says he takes vacation early, does he finish early or does he fall?
Oh, yeah. That's a little bit dark humor there.
Yeah.
We're gonna do as many as we can. Yeah. Yeah. All right. So, so rank in terms of inertia. Like, if you have a small weight versus a large weight, and you put the same force on them, you guys think the large weight's gonna barely move, and the small weight's gonna fly across the room, right? So the more mass, the more resistance to motion. So 33A. Let's rank masses. Okay. So do you guys think looks like the 15 kilogram iron is the most mass? Okay. So mass B is the most because that's 15 kilograms. So that's more than what's next? Looks like the sand. So the mass A, which is 12 kilograms. Okay. And that's more than the 10 kilogram water. So that's mass C. which is 10 kilograms. And that's more than mass D, which is the pillow, which is 2 kilograms. Okay, boom, 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 just like that. Okay. Part B, rank the normal forces from greatest to least. Oh, the normal force. Is that the support force from the table? Should that just be equal to its weight? Just the opposite direction, right? So do you guys think it's probably the same rankings? Same rankings, right? That's a different concept, but should be the same rankings, right? Because they're all just sitting at rest, so nothing crazy going on. So I think the object's gonna go B, A, C, D again. So this time it's weight. So force normal on object B, which is, guess how many newtons would that be? Here, guys, 15 kilograms weighs how many newtons?
1.5.
Wait,
1.5.
is weight equal to mg?
Yeah.
M is 15, G is 10.
25. It's 35.
Here, here, weight,
Is 100, right?
huh? Here,
15.
weight is equal to 150, 150. Aha, yeah. Okay, so guys, if you got 15 kilograms, it's in a gravity field of 10 meters per second squared. That's a weight of 150 newtons, right? Sure. Yeah, so going from mass to weight at the surface of Earth, you just either multiply or divide by 10, depending on which way you got. Low meters per second, 10 meters per second squared. Right? So yeah, so on Earth, 15 kilograms weighs about 150 newtons. Right? So if the weight's 150 newtons and it's sitting at rest on the flat table, you guys think the table is also supporting with 150 newtons? Right? That's what this is here, the normal force. So let's go 150 newtons. That'd be more than the normal force on object A, which is 120 newtons, more than the normal force on object C, which is 100 newtons, more than the normal force on, I think the pillow was object D, which is 2 times 10 is 20 newtons. Okay. All right, everybody all right? All good, all good. Number 36 is the next one that got shuffled over here. Let's do 36. Okay. Ooh, this one takes some thinking. This is a fun one here. We got Nelly hangs motionless. Okay, so motionless, is that equilibrium? What's the net force equal to? 0 from a clothesline. And do you guys see that the left clothesline is kind of steep and the right clothesline is like more horizontal? Right. So question, which side of the clothesline has a greater tension? The one that's more vertical or the one that's more horizontal? We can solve this with a diagram, the picture. I think we're about to find out. Okay. So 36. Let's look at at a point where all the ropes come together. Okay, so guys, put a dot in the middle of your paper where all the ropes come together. Now let's introduce a Cartesian system. So we'll think, right, gravity's pulling vertically, and then here's parallel to the ground, horizontal. Right.
What was the Cartesian system?
Oh, like XY axes. Okay, so like X, XY could be like Cartesian coordinates, right? So you can like make graphs and sort of thing. Except this time we're thinking like what's vertical and what's horizontal. Okay. Let's get some forces going. I see one rope is pulling pretty vertical. So I'm going to exaggerate that a little bit more than the picture and have it going pretty well vertical. That one's going kind of horizontal. Now, guys, the one that's going sort of, now it's not straight horizontal, but more so than not. I'm going to draw that kind of short. And I'll show you guys why when I finish this diagram. Right? Now, there's a third force, which is the weight. And the weight pulls straight down. Isn't that true? Okay. So if you draw it completely correctly, it should look pretty similar to what I drew. And I'll show you guys why it goes like this. It's this guiding principle right here. The sum of forces horizontally, so say in the x direction, goes to 0 newtons. The sum of the forces vertically, let's call it the y direction, also goes to 0 newtons. That's Cartesian. Horizontal is x and vertical could be y. That's your guiding principle. Now, I know there's three forces. Okay, the weight is already aligned to the axis, so that's nice, right? But what about the diagonals? I'm gonna break these into components. So the one that's fallen up to the left, well, it's kind of up, kind of to the left. And the one up to the right, well, it's kind of up, kind of to the right. So let's do that. Up to the left, dash some components, up to the right, dash some components, left, up, right, up. You guys see that? You guys got it on your paper too? Okay. All right. Now, how does that align with this guiding principle? Let's go through bit by bit. Right. So the sum of the forces horizontally zeroes out. Hey, do you guys see how my two horizontal components exactly zero out? This one pulls left as much as this one pulls right. Left and right cancel. You see that? All right. How about my verticals? The sum of the forces vertically goes zero. Oh, I think that's true too. Like guys, suppose this was a, I'm gonna make up a number. Suppose this was a 10 Newton weight. Could this be maybe 8 Newtons and 2 Newtons? So that 8 and 2 cancel out the 10 down. So that matches too. You see that? All right, are we good? All right. Now, to go back to the actual question was which tension is greater, right? Guys, which tension is greater? The tensions are proportional to how long did I draw the vector arrows. So I got a left tension and a right tension. Guys, which tension is bigger? The left tension. That's the answer. The left tension is greater than the right tension. Yeah. So if you said left tension, yeah, you got it right. Left tension is greater. Right. The one that pulls more horizontal is going to be less tension. One that pulls more vertical is going to carry more of the weight. You can think of it that way. It's going to be more tension. Did you do a multiple choice? 36. Which, oh yeah, okay. Yeah, so option A, right, would be the left. There you go. All right, over here, number 49, I think is the next one down here. 49. Yeah, okay, and then we'll go hit these, I'll hit these. 49. Why do you seem to lurch forward in a bus that suddenly slows? Right, okay, a bus, a car, so you're going along, and suddenly driver slams brakes, and it feels like you're thrown forward, right? And then there's a follow-up question, why you seem to lurch backward when they pick up speed, right? Well, what law applies here? So, 49. 49. Let's get a vehicle going. Maybe it could be a bus, maybe something like that. On bus wheels. Okay, and it's moving forward, some velocity, and suddenly you come to a stop. Right, now I guess you're sitting on one of these seats, right? You feel like you're thrown forward, right? But really, guys, really what's going on, and hopefully you're wearing your seatbelt. Are you wearing your seatbelt right here? Wearing your seatbelt? No. Oh, okay. Yeah, if a bus doesn't have a seatbelt, I guess, right? But if you're in a car, you definitely wear a seatbelt. So that, because when that car comes to a stop, you feel like you're thrown forward. That's relative to the car. But what about from the point of view of like this guy's standing outside? Say he's like looking through the window. Here's a window. This guy's standing in an inertial frame of reference that's not accelerating. Okay. Does this guy out here see you just trying to be moving at a constant speed and the vehicle itself slows down? Right. So when you lurch forward, right, or go backward, here I'm going to answer both questions with the same premise here, which is, guys, what law of motion does this refer to? Inertia, exactly, right? This is Newton's first law of motion, also known as law of inertia. Yeah, thank you. Right. Which is let's say you tend to move at constant velocity. So when the vehicle call it a bus. So when the bus, say, slows down, you seem to move forward relative to the slowing bus. Maybe something like that. Okay, but we'll just do about that much for that one. Okay, because then when the bus is speeding up, you feel like you're thrown back in your seat. It's kind of the same process, just backwards. So I think that should pretty much cover it. Right? But that's all an application of Newton's first law of motion, law of inertia, right? So, right. So while you guys are finishing writing that, I'll go back and just say what I said again, just so you get to hear it one more time. Right? This guy standing outside the bus is an inertial frame of reference. This guy inside the bus is in an accelerating frame of reference because the bus is slowing down, or later on maybe speeding up, but it's changing speed. Okay. So this guy outside the bus, let's call this guy Bob, and let's call this guy Alan. Okay. So Bob's looking at Alan, and from Bob's point of view, Alan looks like it's just moving forward at constant velocity. As long as the bus is going constant velocity, then it's all good from Alan's point of view. But when the bus slams on the brakes, Bob sees Alan still trying to move forward at constant velocity, but now the bus is slowing down relative to that. That means Alan, relative to the bus, feels like he's thrown forward. Okay. All right, so you guys good with the bus? All right, next one.
52.
52. That's right. That's right. Which of the following are scalar quantities and which are vector quantities? You guys remember scalars and vectors. Guys, what property does a vector have that a scalar does not have?
I don't think we've gone over the scale.
Guys, what do you know about either of those?
Nothing.
A vector has a what and a what? A direction and a magnitude. Exactly, a direction and a magnitude. All right, so 52. Here, I'll remind you guys. I'll jot this down. Here's a little bit of notes. A scalar quantity has only a guys. A scalar has only a what? Magnitude. Okay. A vector quantity. I'll leave a little space so we can do some examples. A vector has both a magnitude. Let's say how big is it? And also a what? Direction. Aha. Okay. That's like when I'm drawing these free body diagrams, I'm drawing vector arrows for, well, force could be a type of vector. Right? Right. So they give us a list here. We got to sort out what's what. What do they do? We got force. Guys, what is force? Is force a scalar or a vector? How about a vector? Force. What's the next one? Ooh, age. Guys, what could how about time? What could time be? How about a scalar? What else we got? Acceleration. Ooh, guys, does acceleration have to have an associated direction? Yep, which makes it a vector. Acceleration. Force and acceleration are both vector quantities, right? In fact, the net force has the same direction as the acceleration. No, it's just like a bullet point star. Yeah, it's a bullet point. Okay. Let's start. What else they give us? Oh, temperature. Guys, what do you think temperature is? Is temperature a scalar? Temperature. Guys, does temperature have a scalar? Sorry, have a spatial direction? No, it's just like how hot or how cold is something, right? Which next semester we'll talk about kinetic energy theory of temperature, like how fast are atoms vibrating, but it doesn't really have a spatial direction. All right, so they got it's got scalars, got some vectors, got some examples.
Wait, so what about?
No. What about which one?
Age is time.
Oh yeah. Okay, yeah. I just wrote time instead of age. All right. Number 56. 56. The Huh?
Equal, right?
I don't know, gotta read this first. Let's say that the rope supports a lantern, 50 newtons. The tension in the rope. Tension of the rope. Guys see those two ropes are pretty close to vertical, right? Maybe not exactly vertical, but they're pretty dang close, right? Now, there would be a difference if, oh, guys, let's do 56 and 58 together. You guys see 58? Let's do these together. You guys see these two ropes are almost horizontal?
Yeah.
And it's the same question. What's the tension of the rope compared to the weight of the lantern? You guys see that? They're different. They're different.
I told you.
Let's do
I'm wrong.
56
Yes, I'm sorry. Yeah.
and 58. Right.
58 is less, right?
Well, let's try this out with a free body diagram. We're gonna find out. So let's get a dot in the middle of the paper for each of these examples. Right. They say a 50 Newton lantern. Go ahead and draw a down vector for 50 newtons. So do mg equals 50 newtons. Mg equals 50 newtons. Right? So we got a 50 Newton lantern in each case. Right? Now on 56, the supporting ropes were pretty close to vertical. So now if they were exactly vertical, then the two upward forces would be exactly how many newtons?
25.
25 and 25. Right. So if they're pretty close to vertical, do you think it's pretty close to 25 and 25?
Those are both straight vertical. That is not an
Pretty much. Right. So this is about 25 newtons. This is about 25 newtons. Right? Yeah. Now, if they're not exactly vertical, yeah, maybe it's like 26, 27, 28 newtons. But it's definitely, I'll say tension, right?
Yeah.
But it's definitely less than 50 newtons, isn't it? Right.
Yeah.
So the tension force could be less than the weight. Okay.
Told you.
Right. Now, what about when they're almost horizontal?
6 is less. 58. Wait, so 58 is more then, right?
Yeah.
I told you.
Other than more tension, more work.
Okay. Guys, watch this. You guys see I drew the tension. This is really long, right? Tension. Right. Now, this one's pulling up left, this one's pulling up right. If I break this into components, here's left, here's right, here's up, here's also up. Right. Little arrowheads, arrowhead. Right. Now, guys, what is this upward component equal to?
25.
25 newtons. This was also 25 newtons. Is that true? Right.
Yeah.
But if you have a triangle, do you guys see a nice right triangle here? And this is an acute angle. Isn't it true that this leg here would be more than the long leg is longer than the short leg? Is that true? Right?
Yeah.
So like once you pass 45 degrees, that would be true, right? And put it all together. So I know that this is definitely bigger than 25 newtons. And then you do Pythagorean theorem. You could attach numbers to this, but you guys see at the end of the day, the tension is going to be more than the weight. Right? You can attach whatever numbers that you want to. That'd be the case. You know what? I got a third question for you guys. I wonder what angle it changes from being less than to more than. What angle?
90. 50. 40.
60. 60 degrees. Oh yeah. I'll show that too. Suppose you got mg is 50 newtons, whatever, right? Because we got a 50 Newton land, right? As if I change this angle from the vertical to 60 Newton, or sorry, 60 degrees, I meant 60 degrees. If this angle right here is 60 degrees, right? And I guess if this one's 30 degrees for that matter. So you know what? Let me add to this story a little bit. Right? This angle has to be less than 30 degrees for this to be true. So I'll say theta is less than 30 degrees. These ropes have to be really getting horizontal. That's the only way for this to be true. Right? If it's exactly 30 degrees, then this tension is equal to the weight. Right? For only that case. Right? Right, guys, right? And you guys saw that, that you guys were in the spring scales lab, had you guys take a couple spring scales, hold a weight, right? If this was 60 degrees, then each spring scale was reading exactly whatever the weight was. All right, what got next here? Okay, we did 56, 58.
61 would be yes, because there's no force acting on
I don't know, I have to read it. So a
61
ball. Oh, we're getting there. We're getting there. We're getting there. The ball is tossed straight up. Momentarily comes to a stop at the top of its path. Is it in equilibrium? Oh, guys, what does equilibrium mean?
equal
The-
force zero.
The zero net force. Zero net force. Right. So number 60. Guys, the ball at the top of the path. Guys, here's the ball at the top. So going straight up, coming straight down. Right. Are there any forces on the ball at the very top?
No,
Yes.
gravity.
It's weight.
Weight.
Mg, right? Which is the only force, which means that there is a net force, which is not equilibrium. Was that the question? Is it, yeah, in equilibrium? So not in equilibrium.
Wait, why?
Because-
it's sort of gravity's pushing down, so it's at zero in midair.
Because net force is not equal to 0 newtons.
What?
Net force is equal to its weight.
So
F
it could never
net.
be in equilibrium.
Equals mg. Huh? Right.
So
guys,
the only time it
okay,
would be in
perfect.
equilibrium-
Huh?
Like someone knocking?
Is there?
I don't know.
Oh, I don't know. Sometimes it sounds like someone is, but
That's creepy.
yeah. All right, so guys, equilibrium is 0 net force. So in a free fall situation, there is a net force. The net force is the weight, which is not equilibrium. Okay. Right. Although, you know what? Tell you what, too. There is a really weird, nuanced answer to this too. When you get to general relativity, like Einstein physics, Einstein would actually answer this the opposite because he had a different perspective on gravity. But we might talk about that next semester a little bit. But for right now, we're gonna say this is true. All right.
Which one is true?
It's both true and not true depending on your perspective. So
So that's the answer for
If
it.
you grow it up.
Yeah.
it's, That
Yeah.
peak there would not be.
Because it still has,
yeah,
so it
so-
still has weight.
yeah,
there's no normal
equilibrium,
force.
you care about forces and accelerations. You don't care
There's
about
no normal
instantaneous
force.
velocity. Yeah. All right.
So 61 would be, it is that equilibrium.
Hockey puck, yeah.
Constant speed, so there's no force.
Let's check out number 61. Number 61. Hockey puck slides across ice at constant speed. Guys, constant speed. Would that be equilibrium?
Yes.
It sure would be. Here, I'll draw you guys a diagram. Hockey puck. Let's move in. Speed. Mg. Normal force. So constant velocity means acceleration is 0. Means the net force is 0.
Because she is at
Equilibrium. There you go. There you go. 60, 61. All right, there's our. Oh yeah, go ahead. Not today. Guys, I want to do all these puzzles with you guys. So this is gonna take us a few days. We got some labs coming up. We're gonna do some more puzzles. Yeah, but that's gonna have to be our pause point today. Here, we'll look at it.